All right, so we're going to talk about true mapping. True mapping. Now, there are just it's just two rules to be able to identify the true mapping. Now, the first rule is that no element in the domain can have two images in the codomain. Remember what we gave? Yeah. Then the second rule is two elements in the codomain. Okay, two elements in the domain can have the same image, but two image can't have the same elements. What do I mean by that? Now, if you have two sets A and set B, you can have let's say 1 and 2, and you have 4 and 6. Now, when you want to map this, let's say a function is relating the both of them and the function maps A into B. According to our rule, no element in the domain can have two images in the codomain, meaning a function cannot map one element in the domain to two elements in the codomain. So this is not true mapping. Stand. But on the other hand, the second rule we stated is that you can have the second rule stated is that two elements can have the same image. So two elements in the domain can have the same image. Let's say if you map this, the image of 1 can be 5, the image of 3 can also be 5, then this can go to this. You understand? So this is true mapping. So the difference between this is that the elements in the codomain cannot have two images. You understand? But the elements in the codomain can have as many elements from the domain as possible. Understand? So let's check out more examples. Okay. Now this is not true mapping because the elements in the domain cannot have three images. You understand? Another example, we can have 1 and 2. You can have 4. This is true mapping because the image, okay, two elements in the domain can have the same image. You understand? The idea here is just that the elements in the domain, they cannot be attached to. They must be attached singly. You understand? To an image. But the elements in the codomain can have more than one element attached to them. Understand? Another example is something like this. You can have 1 and have 3 and 4. This is true mapping because the element in the domain has just one image. Understand? So we move over to other terms we need to discuss. We've talked about equal functions. Now let's talk about the range of a function. What is the range of a function? The range of a function. Now the range of a function is a collection of elements in a codomain that serves as an image to the element in a domain. Understand? Let me give you a pictorial representation. Let's say you have this is A, and you have this is B, and a function is mapping A into B. Let's call the function H. Now we have 1, 3, and we have 2, 4, 6. And this is mapped to this, and this is mapped to this. Now, the range is just all the images, or all the elements in the codomain that are mapped to something. So the elements here that are mapped to something is just 2 and 4. So the range of f is denoted this way. It writes the function. So we're using a function h of a. You use the domain. So you state the images. This is 2 and 4 in a set-like manner. Stand. So let's go to one-to-one function. One-to-one function. Now it says here, no two different elements in the domain have the same image. What do I mean? From the word one-to-one, meaning if there's a mapping, everyone must have their own image. You understand? Remember we said something about true mapping. C, D, E, F. We have Y, A, B, C, D. And we have a function. Let's say F. And this function maps, let's say, C to B, D to C, E to D, and F to A. Now, this is a one-to-one mapping. What do I mean? Remember when we talked about true mapping and we said the elements in the codomain can have, the images in the codomain can have two elements linked to them, you understand? So let's say we have C, D, E, F. We have A, B, C, D, X, and Y. I have a function linked to both of them, F. So now, if this is mapped to this, this is mapped to this, this is mapped to this, and F is still mapped to C. This is a true mapping, you understand? It's true mapping, but it is not a one-to-one kind of function, understand? So this is the difference between I just need you to like get the idea from the name one-to-one. One element, one image. One element, one image, you understand? So this is not one-to-one mapping, but this is one-to-one mapping. So let's talk about another thing. Let's talk about onto mapping. Onto function or onto mapping. Onto function. Now, onto just means that every member in the codomain serves as an image to something. There is no member in the codomain that is left out. What do I mean? You can have A, B, C as the domain, and you can have E, F, G as the codomain. So if every member of the codomain is an image of something, it is an onto function. Let me give you an example of something that is not an onto function. So let's say A, B, C. You can have E, F, and now, okay, E, F, G, sorry. E, F, G. Now, if this is mapped to this, B is still mapped to E, and C is mapped to G. This is not an onto function. Why? Because F in the codomain is not serving as an image to anything. Let me give you another example of an onto function. You can have A and B. You can have E, F, G. This is mapped to this. This is mapped to this. Now, this is not an onto function. You understand? This is not onto. But this is one-to-one. Understand? This is one-to-one, but this is not onto. Understand? It's one-to-one because, as we said, no two different elements in the domain have the same image. Understand? They have different images individually. Now we go to identity mapping. So we'll go to identity mapping or identity function. Now, identity function. Now, the function of an element in the domain gives an identical image in the codomain. It's just very, very simple. It means that if you have a function, let's say A, okay, let's say sets A and B, and a function maps A into B. Remember what we said? We said that a function usually comes with an equation, you understand? So let's say we're given elements 1 and 2. And let's say when you plug in these elements or these members into that formula, let's take a formula into that formula and you're meant to get their images. You still get the same thing, 1 and 2. Understand? So these are identical these are an identical function, or these are an identical mapping, where the element in the domain gives an identical element in the codomain. Understand? It's just very plain. The arrangements can differ. 2 can be up, 1 can be down. It doesn't mean. Understand? Now we'll talk about constant function. Constant function. Now a function is said to be constant if all the elements in the domain have the same image. Very straightforward. This is an example of a constant function. And we can have A, B, and C. Over here you can have 1, 2, and 3. A can be mapped to 1, B can be mapped to 1, and C can be mapped to 1. This is a constant function because all the elements in the domain have the same image in the codomain. Understand? Now we go over to products or composite functions. Products or composition function. Products or composition function. Now let me give you an instance here. If you're at this point and you're asked to get to this point, let's see, there's a route that leads this way. Okay, let's just erase this. Now let's say you are standing here and you are expected to get to this place, yeah, but there's no route that leads straight from here to here. So let's say there's a route that leads this way and then this way. Understand? So what you're going to do is you're going to first of all move down to this point, get to this point. So this is just like your half. Then After getting to this point, you now move to this point. You understand? So this is, let's assume that you need a function or you need something to move you from this point to this point. Let's say a function, let's assume a function f. Now you need another function to get you from here to here. Let's say a. Remember we said function can be anything. Let's say you need a bicycle to get you from here to here. Let's call the bicycle's function f. You need a car to get you from this point to this point. Let's call the car's function g. Now, rather than going through this long process, making use of function f and g, let's say there is a railway somewhere and the railway connects you from this point directly to this point. You can see that the railway on its own is a function. Now, okay, let's call the railway h, the function of the railway h. Now, instead of going to this point, the bicycle, and then going to this point with the car, at the end of the day, you're getting from point A to point B. Why not just move straight through with the railway and get to your desired point? You understand? So this is just like a shortcut, you understand? A better way of moving. So this train, the function of the train covers the function of the bicycle and the car. Understand? So how does this relate to product or composite function? We're going to see it now. Now let's say you have three sets. Set A, you have set A, and you have set B, and you have set C. Now let's give each of them elements. So let's say A, B, C. Let's say X, Y, Z. Let's say R, S, T. Now let's say set A and B are linked together by a function. Let's call this function f. Set B and C are linked together by a function. Let's call this function g. Now, obviously, remember what we said. We said what a function does is map the elements in the domain to the elements in the codomain. So what the function f will do, okay, let's use a different color for this. This is g. Now, what the function f will do is map the various elements in this domain to the elements in this codomain. So let's say we map element C to Y. Let's say we map element A to Y. And let's say we map element B to Z. So this is mapping. Now, function G maps the elements of B into C. So let's say G maps X to R. G maps Y to T. And G maps Z to R. Now you can see that this is just like the illustration we gave. You're trying to get from A to C, but you go through using two different functions. Now, what if there is a function that just leads you directly from A to C? Let's call this function, let's call this function h. Now, h is a function gotten by the product of these two functions. Understand? H is a function that maps A directly to C. Understand? So it's a product of these two functions. Now, that's why we are talking about product composition function. Understand? So how do we denote H and how do we apply this stuff in our calculations? Because yes, definitely there's calculation under this. Now, this is how you can denote, another way of denoting the function that links A directly to C. So you're going to be working with the last function. So you're going to have A can be written as the product of, now it's written this way, G of F. This is how you write it. You start with the last function, then you go to the first function. So it's G of F, understand? So this is a function. So in order for us not to get confused, because we're going to be using this a lot, so the function that maps A directly to C is function G of F, a combination of the two functions, you understand? Now we're going to try to apply this. So let's say we have a function. Remember when we were studying functions, we said if a question comes to you this way, F of A, what would you write here? You're going to write the image, you understand? Remember what we said, to denote image, you denote it this way. Write the function, write the elements in the domain, then you write the image. The image of A is Y, understand? But we're not making use of this now. We've gone past that. So what we're making use of now is the composite function or composition function. So G of F of element A will give us what image? Remember, we are linking A directly to C. You're bypassing B. So if you trace, element A is mapped to element Y, but that's not what we're asked to look for. Then element Y is mapped to element T. So G of F of A gives us T. So the next, G of F of B gives us, now you trace again. It gives us B, but that's not what we're looking for. It gives us Z. So Z is linked to R, so we have R. Now, thirdly, G of F of C is going to give us what? Now you map it. C is linked to Y, and Y is linked to T. So this is the function of a composition function or a product function. It just combines two functions together and you work with it. Or another way of representing this is another way of writing G of F, you can write it this way. You can write G of F of X. But let's not get into that. When we want to calculate, we'll make use of this to avoid lots of confusion. So this is just what a composition function is. Now we're going to go to calculations to try to figure out a lot of things, how to apply that knowledge. Now a question can come this way. They can say, example, if f of x is equal to x squared and g of x is equal to x plus 3, find I f of g of 2 and I g of f of 2. Now solution. This is going to prove if f of g and g of f is the same thing. Remember when we were trying to denote how you write it, we said you write the one at the extreme first before this one, understand? So we're going to determine if that has any repercussions if you don't do it that way. So we'll take the first question. Now f of g of number 2. Now if you are, let's assume you're asked to look for f of 2. It's just going to be easy. You just plug in f of 2. If f of x is x squared, f of 2, you just substitute x and you have 2 squared, right? This is very, very easy, straightforward. But now you're asked to look for a composition function. So what you're going to do is you're going to break this down into parts, you understand? So f of g can be written this way. So you write the first function f, then you write a function of g first. So So this is how you can represent this. So the first step is to do this. Now the next thing to do is you're going to solve for this, the one inside the bracket. So if g of x is x plus 3, that means g of 2 will be what? 2 plus 3, which gives you 5. So you substitute 5 into this, you're going to have what? F of what? 5. Now, you can now use this to apply here. So if f of x is x squared, f of 5 will be what? 5 squared, which gives you 25. So this is the answer. So the answer for f of g of 2 is going to be 25. Now we're going to check if this is also going to give us the same answer. So let me quickly erase this. Okay. So g of f of 2. Now the first step is to write g. Then you open your bracket and you write f of 2. Now we're going to solve for f of 2 first. So f of x is x squared. That means f of 2 will be 2 squared, which gives you 4. So you're looking for g of what? 4. Now if g of x is x plus 3, g of 4 gives you 4 plus 3, which gives you 7. Therefore, g of f of 2 gives you 7. Now you can see that there's a difference between f of g and g of f, so don't make the mistake. Yeah. So we're going to go to, there's something we need to state. Now when they say the associative property of something, it's just like trying to represent if you have three things, A, B, and C, trying to multiply each other. It means that if you do A times B times C, it's going to give you A times B times C. Like if you do this together first, get an answer, multiply by C, get an answer. If you try the same thing, A first times something, is going to give you the same answer. So this is just a summary of what associative property of product is trying to talk about. So let's relate this to functions. So for product functions, if you have three functions, h, g, and f, the product of h of g, of f, and h of g of f. Now if you solve h of g first, then you add f, or you solve g of f first, then you add h, it's going to give you the same thing. So you just need to note this down. Yeah. So we'll proceed. Now we're going to talk about inverse functions. Inverse functions. Now, inverse functions exist for one-to-one mapping. Understand? Inverse functions exist for one-to-one mapping and onto mapping. What do I mean? If you have a function, it's just very easy. Let's say you have two functions, A and function B. We have A, B, C. We have X, Y, Z. A is mapped to Y. B is mapped to X. And C is mapped to Z. And okay. C is mapped to Z. And let's say we have a function that does this and maps each of them. say function f. Now the inverse of this function, the inverse is just like, let me say, the opposite. So the inverse is going to be f. Okay, it's just going to be f prime. Understand? The inverse. So the inverse now will just turn this whole thing. Now for the inverse of this function, b becomes the domain and a becomes the codomain. So b now becomes the domain. B will have x, y, z. And we have a as the codomain. We're going to have a, b, c. So the inverse will map b into a. Inverse function f prime. Map x to b. We'll map a to y. Okay, y to a. And we'll map z to c. So this is just what inverse function is talking about. Now, a function which is not one-to-one, inverse function does not exist. Understand? For a function which is one-to-one, let me explain why that is. Said for a function which is not one-to-one, the inverse function does not exist. Now let's say we have a very simple function, a very simple set a and b. We have 1 and 2, and we have a mapped to 1 and b mapped to 1. Let's say we're working with a function, g. Now the inverse of g, which is g prime, this is not, mind you, this is not one-to-one, you understand? Because two elements have the same image. So when you want to have the inverse now, you want to have something like this. 1, 2, 1 and 2, then a and b. 1 will be mapped to both a and b. The inverse function g prime. Now this is not true mapping. Remember when we said something about true mapping? We said an element in the domain cannot have two images. So that is why inverse function only works when it is one-to-one. You understand? If it's not one-to-one, it cannot exist. You understand? And this is not okay. Yeah. So there's a calculation under this. There's a calculation under remember, this is just like the pictorial representation. There's a calculation under inverse functions, under range, and under domain. So in the next video, we're going to talk about the calculation under this, which is inverse function. How do you apply that in calculations when you're given an equation? Talk about the domain. How do you find the domain of several functions, and how do you find the ranges of several functions? I'm going to talk about the ways of denoting them, the interval notation, and we're going to talk about that.